First, we're going to talk about plasma models in general. I think Ben's talk at the end of this session here, he'll go into a bit more detail about plasma as well. So plasma models, there's a bunch of different applications for this. Here's everyone's favorite toy, right? Solar physics, fusion physics, manufacturing, thrusters, everything in between. There's lots of applications. So what exactly is a plasma? It's a large collection, very, very large, I should specify, collection of atoms that have dissociated into ions and electrons, which are charged particles, ions being a lot heavier than electrons. And this availability of free charge is what makes this a bit difficult to simulate. So the fields are going to dictate the motion of the particles, and likewise, as the particles move around, the fields, of course, become altered. So here's kind of a cartoon, right? Here's a magnetic field pointing to the right there, and a particle moving through it does this kind of loopy motion. And likewise, if you have a current, this is like current coming in and out of the board there, it generates a magnetic field, and this is just standard Physics 101 type stuff. Anyway, so this makes it pretty tough to simulate this coupling. It'd be really great if what we could do is actually at this point model every particle in the plasma, but we know this is completely impossible on our current machines now and in the foreseeable future. Computational limits are exceeded just even in the smallest plasma trying to do all of the particles. So instead what we do is we model this as a continuous distribution function f in phase space, where the phase space consists of 3 positions, 3 velocities, and a time. Not too important, but what really matters here is the way it's normalized. If you were to integrate over all of phase space, you get the total number of particles back out of this thing. And something that plays a really important role is velocity moments, or I might just refer to them as moments here, where all you do is you hit the distribution function with a power of the velocity, and you go ahead and you integrate that out. And when you do that, you get back to these physical quantities down here. So here's the 0th moment is the number density of the plasma. The momentum density is the first moment, and then energy density, more people would call it stress, but energy density is a fine one for us. Okay, so what's the fundamental set of equations? This is called the Vlasov-Maxwell system. And just like I said, this first equation, this is the Vlasov, and it says how the plasma is affected by a electric and magnetic field, E and B. So if there's an electric and magnetic field present, that updates how the plasma moves and where it is in phase space. And likewise, down here shows how that plasma couples back into the standard Maxwell's equations. That's what these bottom 4 are. And for those of you that are more comfortable with these fluid parameters, those velocity moments I talked about before are actually what show up here. So this is really that 0th moment, and this is really that first moment I talked about, number density and momentum density P there. So this is kind of the starting point for all of our models. And if you take a step back and you look at the 2 different ways of doing this, there's probably many, many more ways to simulate these, but the 2 main ones are a kinetic model and a fluid model. And in a kinetic model, what you do, people should think particle and cell here, PIC methods, is that you actually discretize the distribution function and you update it via some sort of kinetic equations, and then you couple back to Maxwell's equations and solve those, and you kind of bounce back and forth between these 2 models to make it work. On the other side of it is the fluid model, which what you do is you first take a velocity moment of that Vlasov equation, and that's going to generate some new fluid system equations that couple directly back into Maxwell, and you can just solve that in one fell swoop. The kinetic models do capture more physics, so this is actually a bit of an approximation, but there's a lot of nice properties of fluid things that we know how to deal with. With that said, we're going to talk specifically about the fluid model in this case, and just as a quick advertisement here, this is really actually focused on a coupling between these 2 types of models using preconditioned Jacobian free Newton Krylov, and that's some work that's being done down at Los Alamos right now. So you can almost think of this as a preconditioner to a kinetic model. But if you're interested, you can see me at the next coffee break and we can chat. Okay, so if you go ahead and you do that process of the fluid system like I mentioned, these first 2, that's really just the Vlasov equation being transformed into fluid variables for the ions, that's the sub I, and for the electrons, sub E. And what you'll notice is that those variables N and P couple directly now back into Maxwell here via the charge density and the current density, which most people are familiar with in Maxwell. So this is our target system. There's actually a few issues with it, that those Maxwell's equations at the bottom support the speed of light, and that's bad for us when we want to be preconditioning a particle and cell type simulation. So we need to go to something called the Darwin approximation here, and I won't go into the details, but what it really lets you do is it gets rid of light waves, but it still allows for charge separation. And the way this is normally done would be to get rid of the displacement current, which doesn't allow for charge separation. And in short, all you do is you take E and you split it into an irrotational or curl-free component and a solenoidal or div-free component. B is naturally div-free. Yes. Okay, once you do that, you'll see we've just gained a lot more equations. There's Maxwell at the bottom. And now I'll refer to it as, I don't say, but this is now the Darwin system, and it couples directly back to that fluid set. Okay, so how are we going to approach solving this? This is the standard fossils nested iteration approach that many of you have seen before. There's kind of four main ingredients, the first being Newton fossils, and that's going to be basically Newton's method on a fossils discretization. We're going to solve each one of the linear systems produced from this with a preconditioned AMG, CG being the main Krylov method there. And we're going to put that then in a nested iteration framework and use adaptive mesh refinement. So all of these are the components of what I would call this fossils approach. So we'll just hit really quickly on Newton's method again. So what we have there is a nonlinear first order system, and our two-fluid Darwin system is of that form already, where we have f of u equals some right-hand side f, where we're going to take f mapping from V to an L to Q, where Q is the number of equations, and V is some appropriate Hilbert space. We linearize with Frichet derivatives, or Gateau. I don't want to get into that debate right now. Yeah, okay. So anyways, you take one of those types of derivatives, Frichet or Gateau, whichever you want to call it. You end up with this, and of course you drop off that second order derivative. Naturally leads to the standard Newton iteration. And for convenience, just call this f prime down here L and the right-hand side R. And we go ahead and we use a least squares approach for solving this, where really we're taking, an argmin of delta in some sort of V space here. And this is equivalent to the weak form down here. This is all standard finite element theory, where what we end up with is this bilinear form on the left, and that's really what we want to look at for a second. So this bilinear form, script B, I'm calling it L here for each Newton linearization, is, if it's continuous, meaning bounded above by these V norms, and coercive, bounded below by this V norm, then we know B is going to be an inner product on that space V. And Riesz representation theorem nicely gives us that we have a unique solution. That's one of the properties here. As well, we know that for any finite dimensional subspace, V super H there, we know that this is going to hold, and choosing a basis then gives us our linear system. So kind of the punchline down here at the bottom is that if that space V ends up being H1, then we know there exists an optimal multigrid solver, and that these linear systems A there that are produced at each Newton step are going to be solvable with a multigrid method. Okay, so I won't go into the details of the other three components of our fossils type approach, but here's kind of a cartoon. Step one, discretize. Using fossils and Newton together, really those two should be one step. This produces a linear system for each grid. We solve it using preconditioned CG with AMG, and then we refine and project that solution up into the finer grid. And you just repeat this process as you go. Here this animation just shows uniform refinement. We, of course, don't need to do that. The fossils functional gives us a great way to do adaptive mesh refinement methods as well, but I won't go into that today. Taking this kind of fossils framework, we go back to our original problem now, the two-fluid plasma, and we're going to take a look at this. What you'll notice is this is where the nonlinearity shows up here. This is really products of P and N with the fluid variables. It's just an inconvenient way to write it, but works for us here. This is now the fluid block diagonals, and here is the block diagonal for that Darwin system. And I'm going to split those up to make it a bit easier to look at. Let these A guys denote the fluid systems and D be the Darwin system there. And that's really the important part. Ignore the off diagonals here for a second, L and U, and we're going to focus just on these block diagonals as we go. So first, starting with that Darwin block, we look at it and we notice there's some really nasty looking constants in here. Epsilon naught, mu naught, it's like 1 over the speed of light, right? Squared or something. We have some dt's floating around, and we look at the formal normal, which for us is kind of just a heuristic way to know how that system, how multigrid is going to behave on this system. And we see that there's some off-diagonal first-order terms here that are scaled by some potentially nasty constants. And so there's a nice observation you can make. You can just introduce left scaling inconveniently as well, denoted R for left scaling, and S right scaling there. And so you can end up just getting rid of all of these physical constants. So when you go ahead and you look at that formal normal, we know that those second order operators are going to dominate and that multigrid should work well on this. We can go ahead and run some tests on these systems. Here's the L2 error for just a manufactured solution. And this is for quadratic elements, so we see it's going order h squared in this case. And the theory, of course, then says that the Fossil's functional reduction here should be going like order h cubed, and we see that. On the right here, here's the unscaled convergence factors for AMG. This is preconditioned AMG, of course. So we get up to 0.96. Once we do this scaling, we drop back down to really nice Poisson rates. And those physical constants, of course, don't show up. This translates to work units as with nested iteration here, levels 1 through 6. 200 work units, which is the cost of a matrix vector multiply, or you can think of that as one Jacobi sweep on the finest level as a metric. So the unscaled guy here, 200 work units scaled brings us back down to 20. That's not really the important part. We have that Darwin block pretty well figured out. The harder one turns out to be the fluid blocks, and this is what they look like. The real issue here is that it's not naturally H1 elliptic. And the theory that we kind of lean on here is that we really want this to be H1 elliptic, so we know that with standard finite element spaces that we're going to get some good multigrid performance there. So what we do is we take this, it's a bit unconventional I think, and we just take the curl of this first equation and we add it into the system as a whole new equation. And because the way that this number density couples in, it looks like a gradient, we end up with just a 0 here. So that completely goes away. So if you go ahead and you follow through and you work out the formal normal of this thing, it's not terrible, but some of the scalings mess this up a little bit and we end up with one of these grad div blocks here. Of course, we said, why don't we go into the same methodology here? Let's scale this thing and see what we can get rid of. So you can actually come up with a scaling for this block that makes everything match, and that the formal normal down here is really, really nice. Some in the multigrid community would say beautiful, that we really like this identity minus Laplacian structure with no off-diagonal blocks there. So this is going to behave exactly like you would expect after scaling. These plots here are just for the electron blocks. Those are the harder ones because the mass is so much smaller. Again, we get that h squared and h cubed reduction. The unscaled system does not perform as you would expect. Even though it is h1, we would probably expect that these curves to bend back over if we took it to a fine enough mesh. But either way, our scaled system recovers that exactly. Here's the same convergence factors here. We go from at worst 0.5 to a 0.13 for the ions, and for the electrons over here, 0.96. You see a lot more savings there because these systems are a lot stiffer. Translation to work units, again, we won't spend any time on this. Ions, 32 work units total, dropping down to 17, not much savings there, versus electrons is nearly 800 down to 20 work units. So this is really, the electrons are really where we're seeing a lot of performance enhancement. And here's a theorem. You guys can all read this really quickly. No. Down here's the summary. That's the punchline. It says with a pretty mild assumption, which says that after linearization, if we look at these block diagonal fluid, the fluid block diagonals that have been linearized, we end up with this extra u prime term on here. And if we know that this is H1 elliptic, then we can guarantee that the entire system, all nonlinearities and everything all together is as well H1 elliptic, and we should see good performance after that. So here's just showing a little bit about that. Here's a simple test that's going to show just a wave propagation, and we do a backwards difference formula here instead of Craig-Nicholson due to the stability requirements that we need for this differential algebraic equation set. So what do I do here? What you're about to see, I'll click, it'll be a video, or I could just play the video while I describe it. Maybe it's better. Here, what you're seeing is number density. I set up a small cluster of ions and electrons, and I shove them to the right in this case. And you see a steep gradient on the back of it form here as it propagates forward. It's easier, I think, to see in 3D here. So that's really what you're seeing. You see this spike up, and then a steep gradient forms on the backside of this propagating wave to the right. And let's see if that works now. There we go. Okay. So here's the results for that. Here's the unscaled system that we deal with here. And you can see the work units rising as that gradient forms, then it kind of flattens out. This brings us up, I think this is 130, somewhere around there, work units for the unscaled system. And down here is, we drop this thing down and it scales really, really nicely. Even with a developing shock front there, we still get a nice flat number of work units. All right. Then there is this magnetic reconnection problem that's a bit harder. That wave propagation one was a bit more of a just kind of trial to see how our system worked. What you do is if you have a tokamak, you look at a cross section of it, you end up with these current islands that form here. And if we just look then at a small chunk of one of those is the simulation regime we're looking at here. And what the theory says, the physics theory says that these things should attract each other, collide, and form a secondary spike. And for those physicists out there in the audience, if there are any, we're using realistic mass ratios, and that's kind of the important parameter of that set. So here is, you'll see the charge density. It's not too exciting. You just have these blobs, and they kind of slosh back and forth, and they blob around. And they go for a while. We won't even play that whole video. All the action actually occurs here in the current density. And this is where the islands now, you'll see they start to collide, and the secondary spike forms in the middle. That's really, really shoots up. In fact, it goes the opposite direction out of plane. So those were initially in. This one shoots out, and they kind of blob around, and it gets really sharp and then drops, and gets really sharp and drops. And if you go ahead, and that's called the X point here in these simulations, if you take that X point and you look at the magnitude of it, this is what that looks like. And what we see here is that this is what's called, you can measure that peak rate there, and it's called the reconnection rate. And so you can compare this with other results, mostly from MHD applications. And if you do that, it matches closely, but this is a two-fluid plasma, so the results are actually a little bit different, and we don't have a good benchmark to compare this to, but it looks really, really similar to what we would expect to see. So now to the performance of this, it looks a little crazy. So this is for each time step here, how many work units are we taking? And you see it kind of jumps all around here. It starts maybe, I don't know, it's 90, drops down to something pretty low when there's not much action, jumping back up. It's kind of a little bit noisy here. And it's a bit hard to see in this plot what's really happening. So if you look at the number of non-zeros at each time step, which of course is different because we're using this adaptively refined nested iteration for each time step, we end up with a different number of non-zeros on each time step. So what I do is if we took the largest guy here and we actually normalize all of the work units to that instead, this is what you see. And I've overlaid the reconnection rate S, a scaled reconnection rate here. So you can actually see that the amount of work units, or where we're doing more work, is actually kind of scales with that reconnection rate, and that's kind of what you would expect. Our algorithm is picking that feature up and having to work a little harder, picking up more non-zeros there. But I can just go into a quick conclusion here. In short, what we've done is we've developed a modification and scaling of this two-fluid Darwin system that ends up producing a nice H1 elliptic system. And what we end up getting is that the linear systems using a Newton fossils approach at each time step, at each Newton solve there, are amenable to multigrid methods, AMG in this case, preconditioned. And the results that I just showed for that full two-fluid plasma reconnection problem, it's an average of 70 work units per time step, which you should think of as that's 70 Jacobi sweeps for each time step to fully resolve this magnetic reconnection problem, which is a little bit difficult. At worst, we see a convergence factor of 0.93, which I know isn't great, but that's the worst we see, and it seems to hold and scale. So it's better than what we have using some other methods there. And special thanks, of course, have to say thanks to the Lano LDRD people there, the COCOMONS project in particular, and Tom Manteuffel, Luis Chicoen for helping with this, and the Grandview gang. So that is it.